very much. It's a real pleasure to be here. Thank you, Stratos, for that very kind introduction. And it's really, I'm really very glad to be here because it's been a while since I've been to Texas A&M, and especially really a joy to be, visiting this institute. It's my first time, and I'm looking forward to learning more about what you're doing, interchanging, seeing some old friends, making new ones. And I wanted to share with you some of the things we're doing. This is actually some things that we're trying to see how much we've developed some toolboxes and some concepts. We'd like to see how they're going to be applied, can be applied to some challenging energy problems. So I'm going to start with something that I always like to do is basically give you some background as what's motivating. So we start off with a model. We start off with a model that you trust, call it a truth model if you like, based on first principles. And from that, people want to use that model to come up with, to improve the real world system that they're looking at. And some knobs that you can turn here are basically going to be things that are functions of time or space and things that are not, okay? And so what we're going to be doing is saying, okay, there are some case studies that people do to basically use with that model. And you can formalize those case studies and even get stronger properties with optimization algorithms. They have actually the advantage that you can say something about how good your solution is and say that you haven't overlooked anything and found the best one, okay? And then again, you can also say that when you do that, you don't need, a guru or, some specialist to do this. Anybody can do this as long as they understand the process that's going on, okay? So that's useful. But that's not enough. What you see is that you're ending up solving that model many times. If the problem is large, maybe too many times, and the complexity becomes out of hand. So what you're going to do is say something different. You're going to say, can I do this without repeated glorified case studies? Okay. And that's basically the picture on the right, okay, where we're going to say, let's basically take that model and put it together, okay, and solve them together, the optimization problem and the model themselves, and do that in one shot, okay? If we can do that, then the complexity is actually greatly simplified, okay? And that's what we're doing. Now, we'll get into some caveats here, but I think that's essentially one of the things I wanted to focus on. So, over the last 40 years, and Stratos has witnessed some of these, participated in some of these things here. You start off with something that starts with this idea here. Don't search. Solve for the optimality conditions directly. Now, these are local optimality conditions, not global ones. Everyone wants the global solution, but what you have to realize is that if you want to do something quickly that scales to large-scale problems, you're probably willing to look at a local solution. And if you really are worried about whether you've overlooked anything, you can get many locals. You can solve for many local solutions. In fact, local methods are actually incorporated in many of the global optimization codes to accelerate. Okay, so what you do is you say, okay, I want to solve those optimality conditions directly. The Newton-based methods to do that. And here's 4 generations of things that I've had the pleasure of working on. Okay. SQP is something that was developed in the late 70s, actually developed in the early 60s, and then had an interesting evolution to make it a classical method, an efficient method in the 70s. In the 80s, it became part of standard flowsheet optimization techniques. It's still there, okay? The 90s, you basically want to expand this to do things like real-time optimization in refineries. Okay, and so there was a variant of SQP that solves much larger problems, up to, let's say, 10 to the 5 to 10 to the 6 variables, but not only about 100 or so degrees of freedom. In this century, okay, there was a breakthrough with interior point methods that breaks the complexity of many constraints with interior point functions, and also allows you to have many degrees of freedom. Okay, and that's basically allows you to do dynamic optimization. And finally, since it's a Newton-based method, what you can do is you can say, if I have a good solution and there's a slight change in the data, I can get to update that solution very quickly, okay? And that's basically SI. Okay, so those are things that we wanted to leverage here. And the thing we can leverage is the fact that they are fast, large scale methods, fast. They work really well if you can get exact first and second derivatives. And as all of the people that are doing machine learning know, automatic differentiation is now a standard thing. So first and second derivatives should be part of everything. And then you can exploit structure, parallelism, and so forth. And now you have efficient solvers that can handle a million or more variables. That's basically what we want to use in terms of output. Okay, so you basically take something where the glorified case study approach is NP hard with a number of variables, and it turns out to be polynomial, and for certain problems that have structure and certain characteristics, it even approaches linearity in terms of the size of the problem. So that's essentially where we would like to go. So what do we do about this? Well, first of all, there are platforms that work well with these solvers. Okay, this is one called Pyomal. There are many others. This is a Python-based platform, Python optimization modeling objects. And so you have ways of formulating the type of problem that you have. You have ways of doing extensions to that problem. And then you have also ways. Right. You have ways of putting those objects together, and then you have a library of different solvers that you can pick and choose depending on the problem type. And one of those is IPI, which is over there. Okay, now what we're going to do is we can take that and say, what are the challenges for computer-aided process engineering? And in particular for energy systems, we're all very interested in decarbonization. Okay, we have to deal with processes with new feedstocks, energy sources, more efficient and sustainable and safe processes. Okay, so the modeling is important, but also finding the best solution for that model is important for different objectives. And it's not one answer. It's a tool for you to basically explore the space with different and flexible objectives for the optimization problem. So for example, finding advanced designs for alternate fuels, and there's a tremendous scope for innovation on conceptual designs, static and dynamic optimization, robustness to uncertainties. And let's see if those tools that we have right now are sufficient for that or can be improved. Okay. So I wanted to start something that is maybe a challenge, but something that a lot of work has been done already. And I know Stratos and several people here have been working on advanced control systems, model predictive control. One of the questions I've asked myself is, I have a first principle dynamic model. How much of that can I actually put into an online algorithm? And that's essentially what I want to do here. So what we have is we have the process itself. We have a controller that is based on an optimization problem shown below. We want to update that model occasionally with data, okay? And what we need to do is we need to solve that model online in real time, okay? So if we take a look at that model, what we're going to see here is we're going to see this thing, okay? This is the horizon, predictive horizon, long enough to allow us to be stable. And then what you're going to do is you're going to say, okay, I need to find the outputs, Y, okay, that are basically going to be driven to a set point, for example, or maybe optimize another objective. I need to find the inputs, U, that are actually going to be dealing with that. And I have some state space dynamic model over here, based on first principles maybe. And that thing has to be solved within one sampling time. Okay, once I solve that, I shift this horizon one step forward. Well, first inject the control into the process, shift it one step forward, and do it again. Okay, and if I don't do it fast enough, the process runs away from me, and so it's no good. So the question is, this is a time-critical optimization problem. What kind of models can we use for that in order to make it work? Well, so over the years, we've actually done quite a bit of work over the last 15, 16 years to do something with these applications. And I wanted to show you a recent one that we worked on. It's a really neat problem here, and I was very pleased to know that Stratos is working on a similar problem with hydrogen, with fuel cells. This is one that was actually put together at NETL. It's a reversible solid oxide fuel cell, okay, very high temperature. And what the idea is simply to say this, okay, what we would like to do is use hydrogen as a fuel, okay, to ramp up electricity production, especially when renewables are offline, okay? And otherwise, when it's off-peak, then what we would like to do is say, okay, let's produce hydrogen with that when the electricity is cheap, okay? So the fuel cell is going to be either a fuel cell or an electrolyzer, okay? And we'd like to figure out ways to make this work fast and go back and forth. In particular, how fast can these systems switch between operating modes? Okay, so it's an interesting problem. It's certainly not a linear control problem, okay? Just the fact that you're going to switch from one mode to another is important. Now, there are other things that are going to be important as well. It's high temperature. It actually has some brittle materials involved for the solid oxide. And what we need to do is make sure that this has a long life. Okay, so the maintenance of this and operability of this is important. Okay, so we're going to take a look at this, and this is the flow sheet. Okay, what you have here is the heart of this, of course, is the solid oxide cell, which is in the red box there. Okay, and so what you have inside here is around it you have pumps, you have heat exchangers, you have your certain feed flow rates of air, and also of hydrogen basically coming out of this, and then of course either electricity that's being supplied or generated as a fuel cell. And what we're going to see here is we take a look at this and we find out this is we have models for this that were developed within NETL. Okay, and they're PDE based dynamic models, first principles on the solid oxide cell. It's basically dealing with 1D fuel and oxygen channels that are basically on the outside of this cell, and then 2D PEN electrodes, okay? And what we're seeing, the key thing, is basically this assembly in the middle, the fuel electrode, the electrolyte, the oxygen electrode, okay? And what we have there, that's basically called the PEN, okay? And that actually has some interesting characteristics because it needs to not to degrade over this lifetime. Now, in addition, the rest of the flow sheet is made of feed exchangers, trim heaters, condenser. Those are things that are modeled as well and actually participate in the control problem, okay? So in addition to that, what we have is we have these a couple of constraints that have to be satisfied. Basically, preventing unintended electrolysis, keeping the cell potential in line, constraints on the trim heaters, constraints on the hydrogen formation, and then concentration. And then as well, what we're interested in is some constraints here that deal with what's going to happen with the inlet and outlet temperatures, okay? And that's going to be to avoid thermal stresses. In addition, what we have is inside this positive electrolyte negative system, we have to deal with degradation, okay? And those require additional constraints, which are these mixed spatial temporal partial derivatives of temperature, okay? And they have to be there in order to prevent thermal degradation. So this is part of the optimization problem. Of course, what we have in as well is that objective function, which is going to be tracking a trajectory on whether we generate power or hydrogen, some stabilizing constraints over here on the manipulated variables and MVs, and then our controlled variables are basically tracking this guy. And then finally, we have other rate of change constraints. And then finally, we have this curvature penalty. It's going to be important to deal with. Okay, so we decided to make this an interesting study. Okay, we thought, okay, there are several manipulated variables and controlled variables that are part of this system, okay, and you can see them from different parts of the flow sheet. And you also see the fact that this could be done with PID controllers. In fact, most people in process engineering think that PID is the answer and will always be the answer. So one of our colleagues, actually a very excellent person with a PhD from Jim Rawlings, basically put together a PID system, cascade system, that was essentially kind of our straw man for dealing with that. And then in addition, we took the same inputs and outputs, MVs and CVs, and then did nonlinear model predictive control. So essentially the question is, which one's better? Which one can work? Okay, so there you have that process, entire process. Here's a case study with the mode switching. Okay, so we want to maximize hydrogen production, power generation, and maximum hydrogen production. Okay, now what we're going to do is we're going to take a solution approach. PID basically has a model here. It's the model representing the plant is going to be just made with PETC Euler solvers, okay, for the PDAs. And then what we have is we have our NMPC problem. And this has 47,000 variables and equations. Here's the sampling time, a little more than a minute, supervisory control. And what we're able to do is solve this problem in about 2.5 seconds. Okay, so that's actually not bad. Certainly fast enough for implementing this in real time. Now, if you take a look at the results, it's the first thing that we see. First of all, what we see is that we do mode switching. And so what we're doing is we start off with the first period over here, and that's basically going to give us making hydrogen. Okay, sorry, our usage generate hydrogen over here. Then we switch, and over here we use power. Okay, this is a negative number here, and we generate hydrogen over here. And then what we do is we consume hydrogen over here. Sorry, take that back. Here we use hydrogen to generate. Okay, over here what we do is so we go back and forth. Okay, and so when we're using power, basically we're generating hydrogen, and when we're making power, we're consuming hydrogen. Okay, good. Now, if you take a look at that, PI and NMPC are pretty much the same, except these orange blips here tell you that PI has some spikes and not such nice properties, but it's not even worth noticing here. What you also notice is the difference in the duties for the trim heaters is a little bit different, but it's not too bad. And the solid lines are the NMPC here. The dashed dotted lines are the PI. Again, not too much difference. Here's something here that's going to be interesting. Here, you notice that the temperature settling times that happen, you see this with the temperatures, is a little bit longer for NMPC. Okay, and you're wondering why. Then you take a look, oh, we have constraints with NMPC that prevent degradation, okay, of that pen. What happened as a result of that? Of course, PI control doesn't have those constraints, doesn't know how to deal with those, okay? But what will happen is, what's the difference in that? Then you see that here. These are the violations of those constraints. If you use NMPC, you see things are pretty smooth. Again, the solid lines are here. And if you take a look at the PID, which are the dashed lines, well, they're a little bit different. And you see these spiky things, especially on the bottom graphic, okay? There, you see these spikes are all due to PID. And if you take a little bit closer look here, what you find out is that those spikes, they persist throughout the entire length of the electrolyte system. Okay. Those are things that are completely avoided when you do this with NMPC. Okay. So this is one reason to put that first principle model in there and then allow yourself to solve an optimization problem with the relevant constraints. Okay, so this is the first case study. Let's go to the next one. Okay, this was one that I thought was a lot of fun because it was motivated by an industrial project. What I was very happy about was not only did the company support this work, but they sent a person to do his PhD as part of this work. And so that was great. And when he came, what we did was we took a look at this and saw, okay, here's a benzene chlorination process. What's nice about this process is that you have lots of byproducts. These are the ones, okay? Dichlorobenzene, different isomers of dichlorobenzene, trichlorobenzene, chlorobenzene over here. All of those have different prices that vary, in time. And what you want to do is based on the market, the demand uncertainty, the demand supply, the demand of this optimization, you want to run the plant over periods that will take advantage of the market. Okay? And that means, you know, you have customers that have certain demands, prices that have to be satisfied. You want to do this as a multi-period optimization problem. Okay, so let's take a look at that. What we've got here is a problem that looks like this. You have for each period these variables here, Zi, that have to be the states and decisions over here. And then you have these variables here, D, which are complicating variables that persist over the entire time. One of those that you can write as in terms of complicating variables are inventories, things that you make in a certain period and you hang around for a while. Okay. And so what you also have is in each period, you have the entire flow sheet model. Okay. So that is part of the term over here. That's basically what you want to put together. Okay, so how do we solve this problem? Well, if you can think, the number of periods depends on how long do you want to plan. So if you want to do this for a year, okay, 12 periods, maybe monthly, or 52 periods weekly, it's going to grow. And the question is, what do you do with an optimization problem that has to cover all of that? Because the complicating variables, D, apply to all the periods. Okay. All right, so let's take a look at this. You do a decomposition. One is an internal decomposition. And in fact, the person that's championed that with nonlinear optimization is Carl Laird, who's here, and he's now professor at Carnegie Mellon as well. And he has developed some things that basically deal with the linear algebra level of this problem. And so you can take it apart. That works extremely well and it parallelizes. One of the minor drawbacks is that it's monolithic. In other words, you have to basically do this within one system, and it's hard to exploit anything outside of that system. The other approach, external decomposition, which has been championed by several people in the community, and I know my colleague Ignacio Grossman is a big proponent of external decompositions. And what they do is basically do things like Bender's decomposition or Lagrangian relaxation. If you do that, that works very well externally, different solvers at different levels, but what happens is you don't get the fast convergence of Newton's method. Okay, so we have something in between. It's called nested Schur decomposition. Okay, this allows you to get the best of both worlds. Okay, and so what we did was basically start off and look at the problem this way. We are going to start with this problem and divide it up into a higher level problem for the complicating variables, which we now call X, and a lower level problem with a bunch of individual period variables over here, and they fit together in a nice way. Okay? In fact, if you look at it this way, what you can do is see that each of these, what we would like to do is solve each of these lower level problems independently and pass that information to a coordinating upper level problem. Now, what does that look like? Well, I'll do a little bit of a cartoon here. This is the matrix of the entire problem, okay? Now, if you look at the top left corner, okay, what you're gonna see is these Ks, okay? That's the solution of every individual lower level problem, okay? So you can make them arbitrarily large and being large, okay? Now, this has a really nice structure to it, okay? And the right-hand side is basically solving the Newton step, okay? This is basically what the internal decomposition does, okay? Now, if you do nested Schur, all we're gonna do is take that right-hand side and solve each individual problem, so almost all of it goes to zero, except for the bottom part, okay? Now, what difference does that make? Well, you're solving each individual problem by itself, and that's why the right-hand side is zero. And then what we can do is say, okay, great. Now let's zero out and pivot through this guy here and make sure that everything is upper triangular so that we end up with this guy M over here and this guy capital M over here. So these two guys over here, okay? Those are actually very easy to calculate. And that's all you need for the upper level problem. So when you go back and put that into the upper level problem, very little information has to be transferred. You solve the other problems independently in parallel. And so that allows you to basically coordinate these things and do that fairly quickly. It's a lot easier to solve than if you have to handle the whole monolith yourself, okay? So given that you have that, here's the problem. We have some uncertain demands, basically in terms of the pricing and the demands from the customers. That's represented here in red by a loss function, okay, that you can put into the objective function. And so what we have is the upper level problem has the sales, the loss function for the uncertainties, the demand side level, inventories, etc., that are coordinated. The lower level problem is this entire flow sheet, okay? Each one of these being done over and over and over again for each period, okay? So, and you see some of the dummy variables, the Q's here and the F's, those are basically carried over from the upper level problem. So this is nice. What you see is as you add more and more periods, this is a log scale, you're seeing this climb. So now you're getting close to 1 million variables just with 14 periods, okay? So we didn't go that much farther. The person that worked on this had to return to his company, but eventually what happened to us, this was a demand curve of 3 of those products that was being made, and the prices changed as well. And so when that thing had to solve, we had to solve this with the decomposition. So the objective value of the direct approach, in other words, if you solve it as a monolith or by the decomposition, you get exactly the same answer, exactly track this line. And what you see here is, this is basically how the parallelism works. What happens is the direct approach for small problems is still faster. But what you see is as the number of periods increases, you end up basically getting more and more. Now, you're always going to have more periods. If you want to do this over a year, weekly, you're going to have 52 periods, which we're not even close to yet. And that's basically the reason to do this. Okay, so this gives you some idea of what you can do with large-scale decomposition. So now let me take it to the next level. Everyone will say, well, what about first principle models? Do we really need them? We all know that there's a big gorilla in the room that is basically saying, no, the answer is machine learning. Basically build a neural net. You can then basically take enough data and model everything, optimize everything. And I'm not being facetious here. I mean, we all rely on those tools, okay? And we're basically also faced with this idea of large language models, okay? And one of the big differences that we're seeing here is machine learning is especially effective and especially pervasive when there is no truth model, okay? Basically, if you want to write an essay or you want to translate from one language to another, you want to do image recognition, okay? There's no truth there, okay? There's basically no alternative but to use machine learning. Okay, so that's the one difference I wanted to notice here. But we do have truth models. We have first principle models. And the question is, what makes them difficult or challenging is the fact that when they get complicated, they're not going to be that easy to optimize. Okay, so what do? Well, most of the time we replace them with a surrogate model, machine learning or otherwise. Okay, and here's some examples of that. And if you wanted to go to a systematic approach, what you could say is, okay, let's use the data to get an experimental design to construct the model. Let's select the kind of model that we want, especially among the machine learning models in red. And then what we have to do is fit that model with a bunch of things, especially things like stochastic gradient descent, which is very popular. Okay, so we've got all of these possibilities here that will replace the truth model. And the question is, if I optimize that replacement, what's going to happen? Okay, is this actually going to give us something that makes sense? Okay, well, most people say, sure, if I have enough data and I can fit this model very well, then why don't I just use that model instead of the truth model? And especially if it's easier to run, easier to solve, okay? Well, are we going to preserve the physics? Well, the surrogate model doesn't know the physics, but if it has enough data, maybe. So let's take a look. So this was something that Dowling, who's now a professor at University of Notre Dame, experienced when he was a graduate student in my group. He said, okay, I want to build a truth model, a surrogate model of the steam tables, okay? And we have some very good thermodynamic models of those, okay? And one of the things you know from ideal solution theory is that, from ideal vapor-liquid equilibrium, is that the enthalpy is, the ideal enthalpy is not a function of temperature, of pressure, okay? So you end up with this relationship here. And it is actually, in most real systems, okay, the enthalpy does go up with pressure, okay? But if you try to fit that data, that is going to be a fairly small slope, okay? And the sign may be a little bit off, okay? And if the sign is wrong, okay, then what you end up with is a different kind of decision from the optimizer, because optimizers, they are very good at finding your errors, and they will cheat to give you the best solution, okay? In this case, because you find what Alex discovered was that when he actually fitted this, okay, he found out that there was an accurate surrogate model to the steam tables that said, make sure you design the largest compressors you can, because they actually generate work, okay? And that's because of this little flaw in the enthalpy, okay? So this is one of the things you have to look for. Even good surrogate models may not lead to accurate optima, okay? So what do we do to control that? Can you still use them because it solve things faster? So this is the idea. What we're going to do is we're going to start off with an accurate reduced model, okay, surrogate model. And then what we're going to do is we're going to solve an optimization problem, but we're going to put some guardrails around, called the trust region, okay? And the trust region basically says, how well am I actually improving the model, the truth model, okay, when I take that step? And so in this case, I'll keep that step inside the trust region, do some trust region management to see if it extrapolates well enough, and then take another step. And I keep doing that until hopefully I converge to something that is the optimum for the truth model. And I'm going to show you a little bit going on here. So this is my surrogate model, this guy. Okay. Now my surrogate model here is R tilde, which I can choose my favorite preference. But it's going to actually have two things. One is called a zero order correction and a first order correction, okay? And W are the inputs, Y are the outputs, okay? And notice this subscript K, which means that I have corrections at each iteration I'm going to use, okay? So what I'm going to do is I'm going to start off and say, rather than solve the truth model, which is on the left, I'm going to solve a problem that has the reduced model, okay? And it's going to have a little guardrail on it called the trust region, which is the lowest constraint in the green box. All right. So given that I have that, will this converge? Okay. And most of the time, what people do is they'll say, take that green box, don't put the guardrail in there, and just solve the problem and then declare victory, write the paper, then hopefully that'll be heavily cited and you're a hero. Okay. Let's leave the guardrail in there and let's talk about what delta K is actually going to be. Okay, so this is the algorithm. The algorithm basically is provably convergent to the solution of the trust region problem. Okay. Now, what you need is zero order corrections and first order corrections there. You build yourself a surrogate model, which is basically over here, which we call a capital linear model. Okay. And then what you do is you check whether you're converged, you solve your trust region problem, you check whether you're improving the objective function or just getting more feasible. You decrease the trust region if it's the latter, okay, or it's not improving. And then what you do is you go back and basically check this again, okay? And what you can say about this is that this converges for any surrogate model R tilde. Okay, choose whatever you want. See, it'll get to use. Okay. Now, this requires gradients from the truth model. Okay, that's the first order correction. We can extend this if you don't have gradients from the truth model. It's a little more complicated, a bit more work, but it still has the same convergence proof, so that's still good. And what we're going to do here is I'd like to show you some examples. So this is basically a carbon capture example. Okay, what we have here is we have a mean-based absorber. Okay, this is some recent work that was done by Alejandro Pedroso. What we're doing here is we're taking flue gas, and this was for actually an oil company was interested in taking its point sources from the refinery and basically trying to do some carbon capture with it. And they were very interested in a mean-based CO2 capture absorption. And they wanted to figure out what's the best absorbent, liquid absorbent to use, okay? And so in this case, what happened was there's the absorber, there's the regenerator over here, your CO2 stream is over here, and then what's CO2 free is basically coming out of here, okay? So that's essentially what we wanted to optimize. And so in this case, what we found out was we said, let's take a look at that. We took a look at several solvents, the MEA, 2-MPZ, and then AFS with PZ, okay, Pyrazine. And what we found was that the optimum costs here were interesting. Okay, so over here, take a look at the capital cost over here, the OPEX here, and if you put them together, you have something called an avoided cost, okay? So this thing basically, this is $91 per ton, okay, of CO2 captured. And if you have to compress this up to 150 bars, then you end up with $139 a ton. Okay, so these are basically for each solvent. You get different numbers here, and this is the best one here, which is these are basically two different solvents, and you can see those numbers. Again, don't hold me to the numbers; they're taken from the literature, or they're taken from with literature data. And again, it's promising, but that's all it says. So this is the size of the problem, okay? And this is basically our truth model result that was solved using this. Okay, now we wanted to say, okay, take that absorber model, which is by far the largest model that is in the flow sheet, and let's replace it with a surrogate model, okay? And if I do that, I'll use this idea here, R tilde is what we change, okay? And now what I want to do is I want to say, okay, there's my model, okay, and it's 46,000 variables, and without the absorber, it goes down to like 4,300, 4,400 variables, okay? And so I'm going to build a surrogate that basically takes care of the rest of those 40,000 odd variables, okay? So in this case, what we did was we chose, I don't know if you can see this very well. Let's see if I can. Okay. What we did here was we said R tilde is equal to 0. In other words, no surrogate model, okay? Just first and zero order corrections, okay? And if you do that, what you find out is after 21 iterations, it converges to the exact same solution as the truth model. That's basically these orange dots, okay? And what you see over here is infeasibility is basically given here by the blue bars. That goes to 0, okay? Great, okay, so that's basically the first thing you can do. Now, that's not very good, and this is not competitive even with the truth optimization. So we started by generating a surrogate model using Alamo. Okay, Alamo it's a very interesting mixed integer approach that generates surrogate models. It's basically linear combinations of basis functions that it chooses. And yeah, it was developed by Nick Sahinidis, and it's a very powerful way of coming up with surrogate models. So that's what we did. And we have lots of inputs, basically, that are inputs to the surrogate. So it took a while to generate this. And we had 1% error as a result of this. And that was going to be our surrogate model. So that's R tilde over there. It's Alamo. And now it converges to the same truth solution, but only in 7 iterations. Okay, and it's slightly faster than it was for the truth model, okay? And so we thought, this is great, this is a good sign, because now we're starting to be competitive, as the surrogate model is not that big. And then finally, what we did was said, well, wait a second, in Aspen, you've got lots of shortcut models, okay? They're not the rigorous models that we needed for the amine-based CO2 capture, but what we did So we said, okay, let's use that shortcut model. And what we're going to do is simply say, take that guy, and that shortcut model is our R tilde, and that's going to be solved in 5 iterations. Okay, now it's a little bit faster. Okay, so you can see this is the scope that we need. Now you're going to say, well, why do this at all? Because I just have to take one of those iterations, and that's my solution. But that's not going to guarantee that you're at the truth optimum. Okay, now I wanted to show you the last example, which is this guy. Take that flow sheet again and say, let's take that absorber and replace it with membrane separator. Okay, so that there's a liquid flowing in the membrane. Okay, and so you have this guy over here that has to be taken care of and designed. This is actually complicated enough that you need a CFD model for it. So what Alejandro did, and this is with my colleague Gregorius Panagakos, who is our CFD person, basically said, okay, let's come up with a way to do this. Okay, so the membrane basically has 4 compartments. Okay, you can see R1, 2, 3, and 4. Those are dimensions that are optimized. These are the models for each of those compartments, basically lumen, shell side, the outer parts, the wet membrane and the dry membrane, which are the blue and the gray. Okay, and so in this case, there's a grid here with 28,000 finite elements, okay, in our CFD model. And so this adds another 75,000 variables to the optimization problem, okay? So let's solve this thing. And when we do that, what you're gonna see is the following thing. This was done where you had COMSOL Multiphysics doing the CFD, you had Aspen Plus doing the optimization, you had Python doing the trust region filter method, and we put that all together. And what's going to happen when you solve this basically is same kind of thing. The reduced model here was Alamo, okay? We didn't have a shortcut, so that's what we used. Now let's take a look. Okay, this is an intractable problem, okay? But when you put it together with trust region filter, this is what you get. You get it to converge, and you can show that this actually converges to something that satisfies the optimality conditions. What you see is the progress of the trust region filter method here converges to this tolerance here, log scale. And then what you see also is the dominant cost here, unfortunately, is to solve the CFD model, but it converges after 23 iterations. Okay. Now, what's interesting about this is that it shows some potential. You look at the avoided cost for CO2 capture. This is without the compression. This is $54 instead of the $73, okay, which is, again, don't hold me to the numbers because they're based on literature data, but it's promising and worth exploring even more. But what we're doing is we're optimizing the geometry of the hollow fiber membrane contactors, and we could basically do that with CFD. And now what you end up with is you have a trust region filter method formulating this. Okay, this was solved with Aspen codes, but we're doing this with Pyomo as well. And this takes about 20 minutes, okay, which is not too bad. All right, so a couple of things to say. Let me just conclude with a couple of things. First, we're going to say fast equation-oriented optimization is reality. And the key mantra is don't search when you do optimization, solve. Solve the optimality conditions. Do it simultaneously with the simulation model, okay? We have fast Newton-based solvers that can do that. We have modeling platforms that allow you to have structured large-scale models. And we can deal with optimization extensions to dynamic systems and those that are uncertain. Okay, what we saw was real-time dynamic optimization with first principles models. Okay, we can maintain stability, exploiting uncertainties, okay? And we can do that even with fast sensitivity calculations to minimize the online cost. We talked about decomposition for structured NLPs, especially this multi-period problem. That was a demand-side optimization, okay? And so that allows us to exploit large-scale structures in parallel using the same Newton-type steps, and basically the same concepts to solve the NLP. And you can select multiple solvers for the smaller, lower level problems. And finally, we talked about surrogate-based optimization, okay? We can have different kinds of models. We can replace them with AI or surrogate models. And we have a trust region filter algorithm to take us to the truth optimum. So that's essentially the story here. And what I wanted to say is that there's a huge potential to solve some challenging applications with this new bag of tools. Thank you very much for your